Okay, so now actually we do have a recording. Finally, thank you OBS Portable. So we will talk about reinforcement learning today. Not valuing corporate bonds, that's a different class. That's not my class. That's one of your classes?
Can we use some reinforcement learning to value a bond?
You could, of course. Sure, why not? Yeah. And it's actually, it is being used, of course, but so, where are we? Where are the AI? Yeah, there we go. Right. By the way, I also added the extra some materials, very nice. I don't know if you've seen this Stanford CS109. Those who are taking probability, especially those who are taking probability, very good course. The teacher is quite good. This is mostly, of course, it applies to, of course, to machine learning, gives you the probability foundations, and also, of course, for you're taking statistics, right? Yeah, so it may help you there as well. So pretty good materials. So just some extra stuff. All right. And again, I mentioned also before the Simon Williamson, who for General AI Advanced, he's very good to follow actually also. Besides, of course, Fireship, of course, right? Right, you guys are all following Fireship, right, on YouTube, right? Yeah. But Simon Williamson, he writes a blog. I forget what was his actual original occupation, but he's kind of like very pragmatic, right? Not just saying everything is great or not saying everything is falling, right? He writes some tools also, right? So his blog is worth following. Okay, but let's talk about today's topic, reinforcement learning. So, in fact, right, also important topic because there's also something called RLHF, right, human feedback, right? We could be in a loop, right, giving some feedback. That's how ChatGPT actually gets so good, actually, right? It's not just a pure token predictor, right? There is also this RLHF layer. Okay, but let's talk about some. We now want to lay out some ground rules, some definitions. So I'll go to my GitHub and I'll see let's see. Sign in again. Knows all my no, it doesn't know this computer I like. It doesn't know my credentials. Oh, and it doesn't know my password also. That's good. And I don't know my password anymore either. Okay, I need my authentication code, which is good. So even if my passwords leak, my authentication code. All right. Okay. 1, 2. No. All right. Those one-time codes change, of course. Oh yeah. So the issue we've seen so far with our supervised learning, right? We learned something from some examples, right? Let's imagine Gomoku, or if you try to make a supervised learning model for a game, right? What is the issue? Well, the issue is that you have a huge number of states to learn from, right? So you say, okay, this position is good, this position is bad, basically, right? You have to build a huge, you need a huge data set, right? For chess, it's basically impossible. I mean, you have some things you can do, right? But in general, you can't just provide this tool, this huge data set. So that's one of the big issues, right? That reinforcement learning is a way around this, right? So let me see, that's some main topics, right? So again, we still have an agent, right? Again, agents everywhere, right? In AI, everything is an agent, basically, right? That makes decisions, right? Or bot, or program, or code, but of course, it's called agents, right? And of course, what else we have is we have environment, right? That's where we are living, right? Again, let's see. Let it wake up. Let it wake up. All right, yeah. So this guy here, of course, is meant to be Pavlov. You probably heard of Pavlov, right? Somewhere in biology, right? What did he do with dogs? Do you remember? right?
Oh,
He had a bell, and he had, I think, candy or something, or I don't know, sausage or something, right?
training them to
Yes, salivate.
respond to.
Yes, stimulus. Stimulus response. Stimulus response. And yeah, no, and these experiments might seem a little barbaric. I think he cut a hole in their stomachs or something like that, right? I don't know if it would fly today, but in those days, I mean, still, I don't know, right? Especially if you, I don't know what your stance on vivisection is. I mean, but they were, they otherwise, I think he treated them well, all right? But the idea was this: you give a sausage, right, and you ring a bell, right, and then you measure how much, how much your, stomach, what acid, stomach acid, whatever your saliva, whatever your response is, right?
Classical conditioning.
Yes, exactly. Right. So eventually, right, you ring a bell, but you don't give a sausage, and it still works, right? So the dog is trained to respond to the bell, basically, right? Even though he doesn't get a sausage, doesn't seem fair, right? But that's how it works, right? That's how we work too, actually, right? That's how it works everywhere, right? Around us, this world actually it conditions us on all these kind of things, right? Like if you want to train yourself to go to, I don't know, take a cold shower, and you, I don't know, what do you want to do in the morning besides taking a cold shower? Sleeping. Well, sleeping, okay, sleeping is not an option, but something fun, maybe a coffee, right? So you could place a cup of coffee by the shower or something, right? Eventually you won't need the coffee anymore. You'll just still take a cold shower, right? I don't know what else, breakfast or whatever, So, yeah, so I've been trying to, my meal daughter, I've been trying to teach sky before screen. You heard this, right? Sky before screen. Meaning you don't touch your mobile phone before you look at the window.
Oh,
Yeah,
oh,
yeah.
oh, that, no, I haven't. That's a good.
Try to condition yourself. You'll feel better. All right. Yeah. Because I'm sure most of us, some have this tendency to look at the phone before looking at the screen, at the sky, right? Especially these days, right? When we are at equinox today, right? We are going to the bright side and going from the dark side to the bright side. Okay, but yeah. So this idea, but again, so this Ivan Pavlov, right? You can read more about him in our notebook, Wikipedia, right? It sort of underpins the reinforcement learning, right? So we have stimulus, we have response, right? So we still have we are reward the learning agent for playing, right? So alpha goes 0. It's a pretty famous example, very recent, only 6-7 years ago. Basically, it's played against itself. Basically played, I don't know how many games, millions of games, but the idea was this: it had sort of like a tabula rasa, had a blank state. It did not have any model of what a good game of Go should be, right? It didn't have any supervised learning, anything like that. It basically had a reward, a reinforcement. It had a reward, basically. What's the reward? Winning, right? And basically played, right? Basically millions of games, if we believe, right? And eventually, basically, it was self-learning, right? It was a adaptive learning system, basically. And but the model, what's surprising, is amazing, is actually it beat a world-class, basically human player, right? Again, things which 15 years ago, even 15 years ago, people said, AI will never beat, is not Go beating a professional Go player is out of reach. Chess, sure, yeah, you use the brute force in chess in 97, right? That is not fair, right? I know. But Go is still, you need something else. But it turns out, not so much, right? Is reinforcement learning, actually you can do it even, there are a couple of ways, because AlphaGo, by the way, there's two things. There's AlphaGo and there's AlphaGo 0, right? AlphaGo had knowledge, had models inside. But AlphaGo 0 basically started with nothing. Okay, we can do it like hands tied, basically, right? I just need the rules, I just need the reward, how to win, and I'll learn it myself. And that's, of course, like most of, almost stuff of science fiction, right? It's, Skynet, right? So, yeah. So, yeah. So it's really cool. It's really cool, of course, right? So, so we learn, because supervised learning has a challenge in a complex environment, right? Because we have too many states, right? So what's a state? State is a representation of the environment, basically, right? Computer, something computers can understand, right? So So it's simpler. So reinforcement learning can actually be much simpler than supervised learning, right? So it's very versatile, very flexible, right? Video games, robotics, poker, right? In fact, one of your next year's one of the guys is doing a bachelor's on poker bot on for from the year above you, right? So we'll see. He's doing okay, but he has had some roadblocks. Hopefully he'll be okay. He'll be defending in April. We'll see how his bot performs. Now, right, there's two major two approaches. So there's a passive one, basically, right? And then there is, of course, the adaptive, the active one. So maybe let me, before we proceed, the main, right? And so this is not in a book, but I'll sort of like put in the terminology. So we have terminology, right? We have Markdown. I'll turn on the Markdown since I'm lazy. I want to enable. No, open menu. Oh, what's it? No. Oh, there you go. It works. No, terminology for reinforcement learning. Oh, it's dead. I want to learn. I want it to turn on. Oh. Yeah, I'll enable since I'm lazy. For reinforcement learning. Yes. So we want agent. Right, agent. Oh, it knew what I was gonna say. Agent. Right. Yeah, hear me. Environment. God.
That's what you thought.
Right. Okay. Right. So is it gonna have state next? What do you think? Let's take a look. Right. Yeah, state next. God, who is doing all the work? Me or the token predictor?
Almost feels like it's like doing some artificial intelligence.
Yeah, is it using my mic on, or is it actually, my brain waves? I don't know. Right. So action, right? Okay. So far so good. Reward, of course, right? Scalar. It could be. It's usually scalar, right? So of course, it's one thing. Basically, how well you do. You have a score, basically. How well you're doing. That's right. So action. What else do we have? Policy, right? That's a strategy. You're gonna be seeing this policy before. Okay. Very good. Very good. Right. On value function, right? So yeah. So value function. Expect cumulative award. What's cumulative? Of course, over time, right? All the rewards before, right? So on the model, right? Of course, that's in general term, right? Model. What else we have? And I think hopefully that's it, right? Right. That's it. Do we have anything else? Reward, action, policy, right? Policy, of course, is usually right. Usually we use letter pi. But I don't know how can I do Unicode for pi?
Can't you do like to the dollar signs?
$2 signs?
The dollar signs and then inside of it slash. No, inside of it
Like that? Like you mean like this?
slash. Before.
I think so. I think this one. Yeah, this
No, the other slash.
the other slash. Yeah, that looks like maybe, and another dollar sign to close it.
Well, I guess it didn't like
Let's take a look what happens. Yeah, it worked. Super. Yeah, but it's not latex. What syntax is that? It's a markdown something, right?
No, latex was the same.
Yeah, so it works. So it depends on, of course, your markdown compiler, basically processor. But I think the GitHub one, then the CodeSpace one works. Okay, so policy is usually pi. For some reason, I really don't like the idea why it's using pi, because it's sort of messes your geometrical sense of pi. But it has nothing to do with, again, right. So it maps, right? Yeah, maps, maps states to actions, right? So, yeah, policy, yeah. All right. Maps. Maybe deterministic or stochastic, right? Oh, trajectory. That's a new one actually, but why not? It's not hallucination. Episode. Less used. I'm not gonna guess trajectory, less used. I don't know. Episode. I have not seen this one too much actually. I'll stay out of that one, but it's possible, right? It's not hallucination, right? So policy. What else we have? There's also something called Q function, right? There's a Q function, right? Trajectory value function. There's something also Q function. Let's not do the Q. Yeah, Q function, right? And of course, how do you say? Basically, it's a Q function. Yeah, Q state A, something like this, basically, right? Yeah. So basically any action given state. Because again, of course, what we're dealing with is that oftentimes your action, right, is not necessarily going to give you the same result, right? You know, you hit your head on the wall, maybe you'll get a blister, maybe nothing happens, maybe you have a concussion, right? You know, your actions, you know, things will happen, right? So, two more things actually I want to add. So, these are actually kind of important. Exploration, yes. Two key things. These actually will be on the final project, right? So, your final project will involve exploration and exploitation. I mentioned these two terms before. On exploitation, right? Exploitation, right? So, oh yeah, there's also discount factor. That's also good. So also all of these things together, right? So that's oh, it's learning. It's learning from us, right? Right. So, yeah, gamma. I think it's gamma, right? It's gamma. Yeah. All right. So we're learning some new markdown tricks as well today. Okay. So that's yeah. So that's a basic big idea. So these are all terms. Again, most of these terms we use in other, not only in reinforcement learning, of course. Right. So let's keep going. So this is we have some nice changes, right? So. Again, there could be some. So we remember our world, the 4-3 world. We had all those rewards, right? So we could do trials, right? Basically, right? So you could see how well it goes, and then maybe you update your utility, right? So you could do directly, right? So basically, calculate the observed reward basically on, you know, maintain like an average of how well you're doing. Basically, if you have infinite number of trials, right, then of course eventually, you know, you'll find exactly by the law of large numbers, you'll find out your true utility. But of course, it's basically like you sort of reduce your reinforcement learning to supervised learning, and this is not really too. You need to do too much estimation basically. So that it's not very practical, right? So for large space basically. So you will, of course, when we talk about passive, right? There's two things. There's passive and adaptive, active reinforcement learning. So passive one is, of course, when we have a simple policy, right? Right. So this is really I made an example here, right? Basic environment, right? Passive learner, right? We have some states, we have some actions, we have a policy, what do, right? We pass all that in, right? And we have some discount, right? And we have some reward function, right? And we have transitions basically. And then we see for each state, what do we have, right? And also, so we visit each state basically, and we basically estimate what are the rewards are, right? So let's look at this. Let's look at this here, right? So it's gonna connect to a learner, right? So basically, we observe transition. A goes right, and you get B, right? So we pass in states A, B, C, D. Extremely super simple, linear, right? A, B, C, D, right? We have policy, right? Example policy A. You have A. You go right, B you go left, C you go right, D you go left, right? Actions left, right, basically. That's all you can do, right? So it's extremely simple policy, right? You don't really need to think. It's a deterministic, right? No probability involved, just very static, right? So you update the utilities, right? And then you can print the rewards, right? You see A, B, C, D, right? And you observe transition, and obviously you will, you know, it will. I mean, you don't even need to converge, right? You'll have the utilities immediately, right? So you know from A, so A has a utility of 1, right? Because why? Because whenever you have A, you always go to B, and you always get 1 candy or 1 apple or 1 Tesla. I don't know, right? So whenever you get a B, you go -1, right? And so that's a reward. B left, right? So observe transitions, right? So how about C, right? C always goes to right, right? It also got D, right? Again, you always gain. However, now let's see observations. Next state, right? state, action, next state, right? And reward, if any, right? So, of course, D we have not trained yet, right? So we have to train D and see what happens then, right? So, extremely simple. We just update the states. And here, of course, there's nothing more to update. Well, let's see what happens here, right? So, if we go A, right, B, right, we still have our observed transition here, where we have here observed transition, update utilities, observed transition, and it should be, right, if you don't have rewards, right, we have a new reward, because we can add some extra rewards. Ah, right. So we can add extra rewards. It's allowed, actually. So A, right, B, 1, right, B, left, C, right, and C, right, D, actually, and you get extra rewards here. So we can update this, right? So, again, notice you don't have to have a 1 here, right? The value, this is completely arbitrary here. Whatever, we come up with some numbering system of the rewards, right? And we had more rewards from A, right, to C. Basically, we had a huge reward, right? And if I do it again, it will change, right? It'll keep changing. Let's see. A is gaining, D is going towards 0, B is gaining, C is gaining. The question is it going to converge at some point? I don't know if it's going to converge. It seems like it's going to, well, there might not be a limit actually to this, right? If you run it 1,000 times, right? Explore, question to do. Explore whether there is any sort of convergence to some utility values. Yeah, that's, yeah. It's going to okay, right. So simple. This is very simple, but it's of course it doesn't really. The minus for this is that the agent, basically, agent is not really learning anything, right? It's learning, well, it's exploring, right? It's exploring the world, but it's not actually gaining any extra. How should I say? The policy is not updated, basically. So main thing is, right, with the active reinforcement learning, right? The learning agent, we can change the actions, basically, right? So, this means that by the rewards we are getting, right? This is actually what's basically where all the research is being done these days, right? So, we don't have a fixed policy, right? Again, when I say fixed policy, it could have been also probabilistic, but meaning it's set, specific, determined, predetermined policy, which is, you know, maybe it came from another model, maybe it came from humans, maybe it came from committee, maybe who knows where it came from, right? But it's actually set. But here, the policy is actually going to change by the rewards. So this is a big thing, of course, right? And so agent gets to decide what to do, right? So we can modify this. Basically, we can as we get more information, as we explore the world, we can also, our agent can start to become better at exploitation at some point, right? So that's the idea. So you introduce this into this for the actions, right? You introduce this idea of changing the decision model, basically, right? So we have predictions basically, and we update them again. We've done this. We've done update the model before, but here actually we can use it. So again, the main thing from today's lecture is to remember about this fact that in environment we have a challenge of how much time we spend learning, right? You guys sitting here in school, right? And how much time actually go outside in the world and making money, right? And you know, and doing other things, right? Exploiting the world, right? It's a trade-off, right? Do you want to finish, you know, after 4th grade, right? Probably not, right? After 8th grade, no, right? You're still here, right? But at some point, right, of course, you are also heading in the real world, of course, and also doing that. Again, what this reinforcement learning calls exploitation, right? I don't like this word, but that's what's your, like, I mean, yeah. I like this philosophy word, flourishing, like, you know, just having a good time, right? I think I like the better word than exploitation, right? So it's a trade-off. So same thing goes for the agent, right? So, right, greedy. So the problem might be, for example, a greedy agent, right? It learns, right? And I remember from our algorithms class, right? You mostly took algorithms class with me. The greedy, meaning it's very short sighted, he has some heuristic, right? But basically, it chooses what's based on the current information, but does not do any exploration. So basically, sort of like it exploits, so it learns as it goes, basically, right? So it's like, yeah, I don't know if you want to learn to drive a car like that. Probably not very good, right? You'll be crashing a lot, right? I mean, it's like they throw you in the water, and you either you swim or you die, basically, right? So there's many areas where this cannot be suboptimal, right? So, so yeah, so so usually, of course, what you want, either, of course, there's some, you have some sort of sandbox, right? But here, you have some limit for your exploration, right? Again, on by the reverse, you don't want to be the guy. There's a famous story when I was in Santa Barbara, like 20 years ago, 30 years ago, of a guy who basically, I think he got an inheritance or something, or it's a famous story, but it's actually was true. There's also legends of this, but I think he got money as long as he was in school, right? And so basically went to school forever, right? He had a investment account, like I think his grandma around or whatever, right? So he got money for school, right? But there's no limit, right? So he basically, I don't know, he got like eight different degrees or something, right? He was like over 60 years old then, but I mean, yeah, I mean, he had a good life, of course, but I don't know, right? But he didn't really do any, he basically, all he did is exploration, basically. He was only learning, right? But he was not doing anything else, right? So, very limited, right? So that's the other one, right? So, you don't want to leave school at 4th grade, and you don't want to also do, yeah, I mean, who am I to judge, right? Right? So, different things. I mean, yeah, it's if it's possible. I mean, of course, another thing, of course, is if we learn all the time, right? I mean, that's why I like teaching, of course, because you learn things all the time, right? Things change, right? So, and again, even after school, right? At the workplace, I mean, you don't really want a workplace where you don't learn anything, right? That's very limited, right? It seems like even if you get paid a lot of money, but you don't do anything interesting, I mean, you don't learn anything, right? It's gonna take away from your enjoyment, right? So that's the whole thing. Of course, here, agent theoretically doesn't care, right, about the enjoyment, but if it's non-human, I mean, non-conscious agent, right? But, right, so here the book gives you an example. If you're a baby sunfish, right, so you have about, oh my god, this is like zeros. How many zeros? 8 zeros, right? So it's 1 to the 1 billion, right? 1 to 1 billion? 8 zeros? Or is it 1 to 100 million? I guess 100 million, right? Chance of living to adulthood. So, baby sunfish. This means that basically you get eaten before you actually reach adulthood, right? So you don't really get chance of exploration, right? So again, for us humans also, the things have changed, right? So you want the safe exploration, right? That's why you're in school, right? You're allowed, again, up to around age 25, 30, even at a new job, right? You're allowed to make mistakes. Right? You might get fired, maybe not, but it's not the end of the world, right? So as time goes by, you get less flexible, right? So yeah, the example of the car is here too, right? So again, the safe exploration is crucial, of course, right? So in general, of course, we don't, again, so when you're doing this, making buildings agent, of course, you incorporate some human knowledge, right? So maybe, right, so like when the self-driving cars, right? Well, first of all, there might be some, again, I don't want to call it supervision, but of course the car is driving, right? First of all, you have the safety of a human supervisor, hopefully. Excuse me. And also, you might have some examples, some human provided operator, basically, human, right, who provides, the initial guidance, basically, right. So, but of course, then it becomes a hybrid model, right. So, yeah, the temporal difference, right. So, again, you learn a model, you have a model, right. Well, model free method, right. So you learn a function, basically, right. On you don't use money. You have a expected total discounted reward, basically, right? If you take in you don't take finance, right? You don't right? Something called discounted reward, basically, right? Again, we know this idea from that we value 1,000 euros today with more than 1,500 euros, in a year. Even though we know that 1,500 euros is more, it's worse. Remember that experiment, right? When you choose. Yes, time value of money. Very good, very good. Right. So yeah. So in a Q learning, actually, there's no transition model. Basically, you just basically learn the outcomes. That's another approach, right? I think actually I made the Q learning agent here. Let's see if it actually works. So we have states again, whatever the states. We have actions that we can do. We have the alpha learning rate, basically, right? And we have some gamma discount factor, right? So what this means is discount factor. This means that so here 0.9 means, yeah. So yeah, exactly what I meant to say. So well, I would say so basically that 100 moves, the reward 100 moves in the future is going to be very tiny, right? It's not going to be zero, but it's going to be very close to zero, right? So again, of course, you can play around with these discounts, right? So of course, because again, that's how it's in real life, right? You don't know your reward, that shiny candy at the end of the, after 50 years, right? Or you probably don't want to work a job which gives you a golden watch at the end of your, when you finish your work, right? In 50 years, right? But otherwise, it's really horrible, right? Yeah, not you discount that factor heavily, right? Yeah, and especially you guys too, right? You look, what's your like a window, future looking window? Year, 2, 5 years? Yeah, I mean, if you're evaluating like a job opportunity or like a project. Yeah, that's okay. But in 50 years, it has to be really golden. I mean, if somebody offer me a trip to Mars in 50 years, I don't know. I mean, I don't know.
I mean, if someone like said that I'm gonna get a trip to Mars after 50 years.
That might be 20. Okay, to me, it personally be like 10, 15, 20 years maybe, right?
No, Mars. I know it's a one-way trip. So.
Yeah.
Mars seems like a boring place.
Yeah.
Go to Venus.
Venus, right? You could go to Venus, right? Yes, live in a balloon, right, in atmosphere, right? Yeah, okay, but yeah, so this is a Q learning agent. I'm not going to go right now into the bot, but you can run the agent here, right? You can learn the new state. So, yeah, so of course, again, we want to generalize, right? Meaning we want these methods to apply to as many for real world, and you don't have all the, we don't have 3x4 world, right? We have a basically infinite grid, right? Multi-dimensional grid, right? If you're doing even a driving robot, right? A self-driving car, right? You need some of these methods will not be very efficient, basically, right? So you need to do some approximation, basically, right? And again, we know how it works. What happened with that Tesla right now? Test like a couple days ago. It was fooled by what? You read about this? The wall. Yeah, the famous like Wile E. Coyote thing, right? The cartoon thing, right? Basically, right? Yeah. It's still a problem, right? But I understand, of course, it's not the issue of maybe of the algorithms, but it's mostly issue of the sensors, because of course the problem with Tesla is that it refused to use lidar, right? It's using only cameras, right? And it's sort of big shortcoming, right? Because like
But is it like you won't have such wall in real life?
yeah, you can say okay, yes. Well, you never know, because of course people do all kinds of nasty pranks, right? So that's the thing, right? In fact, well, no, you won't have exact wall, but the thing is, of course, sometimes you have some weird ads, right? Some things which might either two things, maybe adversary, right, or maybe just innocent, ad or something which throws like a picture of, I don't know, car or wall, right? I think I showed you this guy. This is not directly related to AI, but the boat. I told you about the boat in San Francisco. A boat painted in San Francisco on a garage, right? Yeah. No. This was no, I can't see, but basically, maybe this was in San Francisco. But basically, it was the guy. I told it was his the housing association told him he cannot keep a boat in a open view to the street, right? He had a yacht, right? And so he said, okay, I'll provide malicious compliance. He hired an artist who drew exactly the same thing you would see from the street, the yacht, basically, and put a wall, right? So now nothing changed for a passerby, right? They still see a yacht, right? But of course, technically,
I guess if you have a yacht in your backyard, then you can afford to do that.
yes, it's of course, it's too much money. It's a first world problem, of course, right? Yeah, it's a first world problem, obviously. But yeah, malicious compliance, right? So what else we want to talk? Well, we almost finished today. So approximate temporal learning, right? The different approaches, right? So spaced repetition, right? You know about spaced repetition. Who is using spaced repetition to learn anything? Anyone? You know what spaced repetition is? It's a psychological idea. To me, yeah, flashcards. There's all kinds of software for this, by the way, right? There's this Polish guy who is like the grandfather of this idea. Like in 1980s, he built the first software, and he learns like anything. It's basically for learning things. You like fix things you don't really want to learn, like facts. Basically, like fixed facts. Like you need some, I don't know, something, right? And the idea is this. Famous things like you study you cram for an exam, like there's going to be an exam, I don't know, physics or I don't know, AI, but mostly, you're learning for something, you studied the day before, right? Of course you're going to forget all about it, right? So if you want to actually really remember something you cram, right, you need to repeat it, like I think it was one day, then roughly a week, then again maybe 3 days in a week, then maybe a month roughly. I mean, there's a formulas for this, right? And then maybe after a year, and then you really, like, somebody can wake you up in the middle of night and ask you, what's capital of Uganda, right? You were doing that? Who was doing that, right? What's the capital of Uganda? I don't know. Right, Nairobi, or I don't know.
No, that's Kenya.
That's Kenya, you see? Yeah, so you see, you don't have your flashcard.
If you would like say a list of cities, and
Okay,
which
multiple
one
choice.
of those is-
Yeah. So somebody wakes you up in the middle and say, okay, which one of these 3 cities is, which one is capital of Uganda, right? I don't remember, But so yeah, so of course, because I'm not using flashcards to learn this, right? I don't care about capital. I mean, it's not my priority. But yeah, but the idea, of course, this is, if you want to learn it, why lose it, right? You're not Sherlock Holmes, right? Who said, okay, he doesn't want to learn something. He wants to forget things. It's not very important, right? But so spaced repetition gives you this power, basically. And there's lots of software for this. There's Anki, whatever, right? There's a whole bunch of software, right? And it's been proven. Super Memo, Quizlet, Anki, you can do your own software. It's pretty easy to do, right? The formulas are there, right? But you can, of course, adjust them, right? Because what you do is, it's basically a form of reinforcement learning, just for humans, right? So, what you do is, you test how well you are doing on this. Do you remember? I'm sure Duolingo does it too, by the way, right? Duolingo does this. Duolingo, who has used Duolingo? None of you? Some of you. What are you learning in Duolingo?
I just came to the conclusion it's not usable.
Yeah, well, it's like I said, it's useful to some extent. I mean, I did like 6 months for German, and I learned some words. But if you're not using it conjunction with something else, it's not that good actually, right? You need to use something else, like some other tools, right? So that's the same thing for here too. What you learn is you learn certain facts, right? Some certain concepts, but you don't learn to use them together, right? So it's so spaced repetition can give you sort of like some basement, some fundamental, maybe some sort of like a fixed knowledge, right? But it's not really gonna be something for logical thinking, right? That's the other part, right? The reasoning, right? So this also can be done in reinforcement learning for agents, non-human agents, meaning computer agents. It can be used too, right? To repeat at some moment, maybe some knowledge that this is a good move to make can sort of disappear from the model. It's an issue with building a model. So you sort of like refresh. Okay, yeah, this might be a good idea to, the move, going from, going to the beach might be actually a good idea, basically, right? So yeah, okay. What else? So deep reinforcement learning, right? Of course, we can do our non-linear models, right? Right, you can build a neural network for function approximator. So it's like use the neural networks from our previous lectures to actually serve as the functions, right? So yeah, another problem with whole reinforcement learning. So like for example, in chess, right? You basically, you play your game and then you get your reward at the end, right? So how do you say if you're doing okay, right? You need some sort of hints, right? So that's where eval comes in, right? A good eval function in pretty much any, gaming activity is crucial. Meaning it tells you how well you're doing towards the goal. Those who play chess, right, usually, pay attention to chess engines, right? There is, like, the best is when you say, okay, mate in 8 or mate in 15, right? This means that the actual AI engine knows exactly the steps to take to make, it's mate in 15 no matter what the other side does, right? But usually, if you do some AI analysis, right, you will see eval scores like -5. No, -5 is bad. You're down a rook, right? But let's say -0.5. That means you're not doing too good, but you're slightly worse. Or plus is +1. That means you're up a pawn, roughly, right? So a simple eval function would be what? Just piece scores, right? So a question: did you guys use eval in your Gomoku? Like some sort of came up? Anyone use eval? Yeah, you did.
Well, I guess, is it the need that I will, min-max?
Yeah, because you need to. Okay, well, of course you can say. So, the worst case scenario, your eval could be just at the end of it, right? You don't know, and eventually you have the the 5 in a row. That's of course the final eval, right? And it's plus 9 million, minus 9 million, right? It's like infinity plus infinity or minus infinity, depending on which side you're on, right? But on the way there, it's helpful. We have some hints, basically, right? And that, of course, is the room. There's room for these eval functions, right? So this is reward shaping, right? So you want to guide the agent towards the progress. So again, like let's say you're learning to play tennis or something, right? Again, how to tell if you're doing better, right? Before you go to your big tournament, right? So there are all kinds of sort of evals, like in a human, right? If you're doing training for anything, right? You need some reward shaping. Basically, you need to evaluate how well you're doing until you get to the final reward, right? So yeah. So what's okay? But there's a risk again. You might. It's like the famous story. I think was there's this book called Catch 22, right? Let me give this here. Maybe AI will learn. There's a famous story. Yeah. Yeah. There is a story in a book. Catch. Yeah. 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 Well, but this is but no, but that's not it. That's fine. But that is not what I want. Where a training officer has a theory that playing, I forget what it was. I have not. It's been like I don't know, a long time since I read this book. Playing something. Yeah. But I don't think it's basketball. I think it's a hallucination. I don't think it's basketball. I think it was like shooting something. I forget what it was. This is a hallucination. I don't think they played basketball. Let me see if I can find it. Then we can finish today. Joseph Keller, right? Catch 22. Training. Yeah. Let me see. Quotes. It's an anti-viral novel, of course, very funny. But I was second World War. Dark humor, black humor, right? So, good. yeah, it's of course quotes. Let me see, catch quotes. I'm trying to see if I can find the quote. But okay, but the whole idea is this, right? All right. He was going to live forever or die in one attempt, right? Oh yeah, he also has that's misattributed. Just because you're paranoid, they're not doesn't mean they're not after you. They're not after you, right? No. Yeah. Yeah. It was miraculous. What is the country? But oh, Snowden, by the way, right? Yeah. But basic idea was this, right? So I guess I can't find the. But basically, that you train for something, right? And this is going to help you in life. It's like, okay, that you're going to learn chess, play chess well, right? It's going to help you in math, or maybe help you in programming, right? Not quite the same thing, right? You can overfit. You can over optimize for playing chess well, right? Maybe you become a chess grandmaster, but it doesn't mean you're going to be a very good programmer or logical thinker in general, right? So any activity, right? There might be correlated activities for something. Like, let's say you learn to run, I don't know, 100 meters really fast, right? You become world-class sprinter, right? It's not going to directly translate to being you a world-class marathon runner, right? So I guess there was a story of somebody who was he wanted to be like the fastest hockey player, so he wanted to start training for like speed skating or something, right? But of course he eventually became Olympic champion in speed skating, but which is good, but of course he never became a hockey player, of course, right? It's like I said, yes, there's things which are correlated, right? But they don't do the same thing, right? So, yeah. So find yeah. So I would like to find a quote, but about the idea this, yes, you become so you train for something, right? And it's often this thing is like this. You see this all the time, right? Oh yeah. This activity is good for kids, right? They will become, they do whenever they play games, right? They'll be good at math, but it's not quite the same thing, right? So that's the issue that I want to bring today to finish this chapter. So reward shaping is, of course, brought with some risks, right? And then the double hierarchical, right? Idea being, yeah. So you want to score a goal in soccer, right? You break it down in goals. Pass, dribble, shooting. All those are individual goals, right? So that might be also an option, right? So because maybe just scoring goal is not really something you can teach directly, right? Yeah. So also you can do some policy search, right? Yeah. So apprenticeship, again, these are all, they use these names which we use in real life as humans, like apprenticeship learning, right? You observe expert, right? So try to build up the model by observing somebody that does something similar, again, right? Sort of like transfer learning, right? So, of course, robust learning from humans, right? Yeah. Yeah, applications, of course, pretty much any game playing, this is widely used because, right, so, and of course, there's a NeuroGAN, TDGAN, DeepMind, right, AlphaGo, of course, is the biggest reward, right, yeah, right, so, and there's an example like here, how to build a model to invert pendulum model, right, right, you want to balance a pole and moving cart, right, so, you have a pole, right, and you have moving cart, so kind of really hard to balance, right, and you have a lot of continuous state variables, position, angle, right, and you want to actually have the have the model eventually balance, right? It's kind of hard, right? You've seen, of course, all the Boston Dynamics videos, right, where they have the robot, right, doesn't fall off, right? No, so it's all built, of course, based on reinforcement learning, right? So what happened? Boston Dynamics. I think they sold, like they were sold to Google. This Google sold somebody else, like last year, I think, right? Something. All that. You see the dog, right? And then of course that whatever the scary-looking quadruped, right? Right? Which you can kick in it, when it gets up, right? All right. So on Monday, what are we going to do on Monday? Monday we're going to do an NLP, natural language processing, right? Which is part of AI, but it's kind of bigger. So we'll talk about some things there. It's something, a field I work pretty much daily, right? Since I do research at library, so very interesting topic. And of course, crucially important these days, of course, because NLP is pretty much, you know, all these things in ChatGPT, of course, is technically part of NLP, right? That's, of course, that's probably for next Thursday, the NLP part. I mean, the deep learning part. Okay, so that's it for today. So yeah, any questions on reinforcement learning? So main thing is, of course, the eval function, right? Coming up with some reasonable rewards. Let me see if I can stop this recording and also